All right, let's see how now we can minimize this function. Like I said, to minimize this function, we should look for points. We should look for theta 1 and theta 2 such that del theta 1 is equal to 0, del theta 2 is also equal to 0. All right, so let's work that out. So the derivative of this with respect to theta 1, I can push theta 1 inside the summation. So I have 1 over n, and then summation of I equals 1 to n. Okay. The derivative of this function with respect to theta 1 is 2. And 2 is the same for every one of these terms. So 2 can come out of this summation. So we can pull 2 out. And then we have the derivative of this expression with respect to theta 1, which is equal to 1, and then multiplied by this expression, theta 1 plus theta 2, xi minus yi. Okay, and set that equal to 0. Before setting that equal to 0, we need to work this out here. So let me just write down the similar expression for this guy. Again, you can push the derivative of this expression with respect to theta inside the summation. Then again, you are going to have a 2. You can pull the 2 outside of the summation. And now the derivative of this expression with respect to theta 2, get an xi, and then this expression. Okay. So now we have these two expressions set equal to 0. Okay, so let's do that. So let me just simplify this expression. Theta 1 and theta 2 are not indexed with the index of the summation. So they're really constant with respect to the summation. So we can pull them out. So if you see an expression like 1 times theta 1, what we can do here, theta 1 is not, like I said, a function, it's a constant with respect to the summation. So you can pull theta 1 outside of this summation. So this is this, then we can pull theta 1 outside. And so this is what this means. Summation of 1. So this means that theta 1 plus 1 plus all the way plus 1. So n of these, which is n times theta 1. And similarly, if you look at, for example, the second term here, that's the summation of I equals 1 to n. And here we have theta 2 xi. Again, theta 2 is constant, so I can pull that outside of this summation and then have this, and you can keep this as this or write it as x1 plus x2 all the way to xn. Okay, so let's use this now to simplify these two equations. All right, let's do that. Okay, so the first equation, like I said, you get n times theta 1. The second equation, we get plus theta 2 times the summation of xi from I equals 1 to n. And then we have 1 times y1, and then the negative sign. So I can take this to the other side and change the sign. And so this will be yi from I equals 1, the summation of yi from I equals 1 to n. So that's the first equation. We can't just solve this equation alone for theta 1 because theta 2 also is in this equation. So we need to write down the second equation, which will also have theta 1 and theta 2. That will be a system of equations that we will have to solve simultaneously to get the optimal theta 1 and theta 2. And here I just got rid of this 2 by n here. I didn't explain that. This is just a constant. This is equal to 0. I can just get rid of that. Okay. So let's work out the second equation. So I have xi theta I, and this one, again, I can write this as summation. Let me actually, to be consistent, let me just replace these two. So here I'm just going to write, I'm just rewriting that, but just replace these two terms. And now the first term here, it's a summation of xi, I equals 1 to n. This is just a scalar number. Once you sum up, basically it's a summation of all the x points. It's just a number here. Multiply with theta 1 plus this term for the coefficient of theta 2 is xi times xi, which is the summation. Just put the index here as well. I equals 1 to n xi squared theta 2. And this is xi times yi, and there's a negative sign. I'll take this to the other side. And then, so this is xi yi. So it's, let me just change the color of the unknowns now that we have derived this. So instead of, I'm just going to change this color to draw the attention to the unknown here. So everything in this pink color is unknown. Everything else in the green color is known. So once you have the data set, you know n, you know how many data points you have, you know all the xi and yi. So all these terms are known. Okay, so the only thing that are not knowns are theta 1 and theta 2. So, and so it's very interesting. You can see the theta 1 and theta 2 shows up in the linear form, right? They are not like theta, you don't have theta 1 to the power of 2. That's a very important distinction. So now the fact that the theta 1 and theta 2 shows up with the exponent of 1, and if we look at this equation, we can actually write this as a system of linear equations and in the matrix form. So we can write this equation in this form. So here, this is n, and this is the coefficient of theta 2. So this is summation of xi, I equals 1 to n. The same term shows up here. And this term shows up here. And then we have the unknown vector. And then we have the right-hand side. The unknown vector is theta 1, theta 2. And the right-hand side I'm just rewriting these terms here. Okay, so like I said, this matrix is known, this vector is known. The only thing that is unknown is the vector of parameters. Okay, so you can denote this matrix by the matrix K, and this is the unknown vector, which we show with theta, and this is the right-hand side vector. So this is a 2 by 2 matrix, 2 by 1 and 2 by 1. So the nice thing is that the size of these matrices doesn't scale with the size of data, it scales with the number of parameters. Okay, so now we can write the solution of this system, and I'm going to show that with the star, because that's the optimal point, is equal to the inverse of this matrix times this vector. Okay, so that's the solution, the optimal solution here. So what does that mean? Like I said, we know K and we know V, so we can actually, these are computable quantities, easily computable quantities. You get this theta star, and this theta star is the one that minimizes the derivative of E with respect to theta 1 and theta 2. So this theta star has theta 1 and theta 2 in it, and these are the points at which the slope of E that at these points will become 0. And that would be the minimum of this function, because this function is really a ball in a theta 1, theta 2 space, and the derivative vanishes at the minimum. Okay, so this theta star is the one that minimizes this total error function. Okay, so and as you can see, this really regression problem was turned into an optimization problem. This is really an optimization problem, and this is the solution of the optimization problem. And in the future lectures, we will talk about how the different ways to formulate this loss function. If you change the formulation of this loss function, if you change the way you measure the error, then obviously you will arrive at a different optimal theta, because theta would be the one that minimizes the other loss function that you have. And we'll talk about this optimization problem in a more generic framework.